Okay, so our first speaker today is Bernardo Zan, who's going to talk about, well, long title, chiral symmetry and mass shift in lattice Schwinger model. Thanks, Bernardo.
Thank you, Alessandro. Thanks to all the organizers for this really nice workshop. I'm going to be talking about a paper that came out this summer, plus some work in progress with people from Princeton, Ross Dempsey, Igor Klebanov, and Sylvie Pufu. I'm going to take things slowly because it's 9:30 a.m., so I'm going to get going easily. And I'm going to be talking about something which is rather old. So we're talking about all these new results in this workshop, but I'm going to be taking a very old model, the Schwinger model, which is from the 60s. I'm going to take its lattice discretization using staggered fermions, which is from the 70s, so this is very old. But I'm going to have something new to say about this, which I think it's pretty nice, and it will have to do with chiral symmetry. First disclaimer, as you see, there's a quote-unquote about symmetry, because I'm going to be talking about sometimes, actually most of the times, I'm going to be talking about a symmetry which is anomalous, so it's not a symmetry. So I should say chiral anomaly maybe. But sometimes I will talk about a symmetry which is indeed a symmetry. I will make sure to point out what I'm talking about. So what is the Schwinger model? Let's start by introducing the Schwinger model. It's QED in 1+1 dimension. So in its continuum, it's a model in the continuum where I have a fermion. So this is a two-component complex fermion, which has some mass. Then I have a U1 gauge field. And I have a theta angle, which in 2 dimension, a theta angle looks like this. This is the Schwinger model. Why do we care about the Schwinger model? Well, we care about it because it's a simple theory that somehow shows some of the behavior that more complicated theories in 4 dimensions show. So for example, this is a theory that exhibits confinement for non-zero mass in the same way as some 4-dimensional theory would show confinement. This shows chiral symmetry breaking, and by this I mean that the fermion condensate has a non-zero VEV in the same way that QCD might show chiral symmetry breaking. But clearly, the reason that we like it is that it's simple. So this is actually solvable in the massless case. So if you're a high-energy theorist, like I am, maybe you're interested in this model for the following reasons. What I'm going to do, and I'm going to show it in due time, but I'm going to consider also its lattice realization. Which means that I will consider a spin chain, which has some quarks living on sites, and some gauge fields living on links. And studying observables of this spin chain in the continuum limit will give me results about the continuum model. And again, if you're a high-energy theorist, this is just a way to do numerics of something that you cannot solve. But some people, especially from the many-body community, are interested in this lattice realization of the Schwinger model by itself for a few reasons. So recently there has been a lot of excitement about simulating gauge theories using numerical methods, and in 1+1 dimension, people like matrix product states or the MRG, the most general name is tensor network methods, which are very, very effective. If you don't know what they are, these are simply some very smart variational ansatz in 1+1 dimension that give you very good result. People like to think about this also in 2+1 dimension and so on, but if you want to come out with some algorithm that describes some gauge theory, you first want to check that your algorithm works well, and you can do this in the Schwinger model while you have some result, analytic result in some case, and you check that your algorithm works very well. So in terms this lattice Schwinger model is very trendy in the last 10 years in this community. And even more, there is another trend, which is the idea of someday it would be nice to do a quantum simulation of a gauge theory. So people would like to put these things on quantum computers, and then instead of doing, I don't know, Monte Carlo or tensor networks and something like this, you go and measure things, and you get your result. And this model has been actually experimentally simulated. So I haven't given the Hamiltonian yet, I will do it in due time, but just n is the number of sites. People simulated this model with 4 sites using trapped ions. So I'm gonna give you also the paper because I think it's pretty cool. It's a Nature paper from 6 years ago. So this model is interesting. What I would like to argue is that the model is interesting both in the continuum and in its discrete version. Okay, but again, I am a high energy theorist, so I'm going to start from the continuum. So let me first give you a bit of a review of what is known about the continuum. And let me start from this thing that I said, that for m equals 0, this model is solvable. And the reason why it's solvable is bosonization. So yesterday we heard a lot about bosonization, and this is sort of the simplest version of that because we're in 1 + 1 dimension. So the idea is that this model has a current, a conserved current, which is this, and I can introduce a scalar field, and let me introduce it like this. Some scalar field phi, and I rewrite this current in terms of phi. You see that the current is conserved because epsilon is antisymmetric. And the idea is I start from this Lagrangian. Every time I find the fermion, I write things out in terms of the boson instead. You can do this. You get a very simple Lagrangian where it's also easy to integrate out the gauge field. So the final result is that you can rewrite this, using bosonization, you rewrite this Lagrangian as this. So you started from a Lagrangian with some fermion and some gauge field, and now you just have the Lagrangian for some scalar field. And I told you that m equals 0 is a nice point in the sense that it's solvable, and indeed, if you get rid of this term, what you're left with is just these two. You can shift phi to get rid of this theta angle, and you're just left with the free Lagrangian for a massive boson. People call this the Schwinger boson. So for m equals 0, this is just the theory of a massive boson with mass e over square root of pi. So the theory is solvable because it's a free theory. For m different than 0 instead, well, I mean, now it's the usual problem of QFT, so this is some relevant operator, and if you want to follow the RG flow at some point, well, I mean, it gets strongly coupled, so you have to come up with some way to study this, and what I will do is instead of following this RG flow, I will study the lattice. So this is the reason why this is solvable. Let me point out one thing that might look like a coincidence, but there's a reason for it, that for m equals 0, the theory doesn't depend on theta. This is just the statement that I can shift, if the mass term is not there, I can just shift phi. This looks like just something that happens, but there's a deeper reason for it, and it's the Schwinger anomaly. This is going to be pretty important because it's what I'm going to think about when I go to the lattice. So let me talk about that. So I told you that Well, this theory has a conserved current, and if you go and look at the m equals 0 theory, you might be tempted to say that there's another symmetry in your Lagrangian, which is doing a chiral transformation on the field psi. But the symmetry is anomalous. That means that it's not conserved at the quantum level. To be more specific, J mu of phi, which is what you would think would be the current in this case, it's not conserved, but instead gives you something like this. And from now on, I will work in the gauge where A0 is equal to 0, and E is the conjugate variable to A1. And it's the electric field. So this symmetry, if you didn't have any electric charge, would be a symmetry, but it's not conserved when you start flowing in your RG flow. And let me be a bit more detailed about this anomaly, because again, that's going to be the main player in the game in what I have to say. So what I would like to do is I would like to see what happens when you do a chiral transformation, what happens to the Hamiltonian. So I want to consider the operator that implements one of these chiral transformation. So Q5 is, well, if the symmetry wasn't anomalous, this would be the conserved charge, so just the integral of J05. So the statement is that this is not a conserved charge, so Q5 and H don't commute. So I want to see what this is. I want to understand why this is the case. And you can start, okay, Hamiltonian, my theory has a fermionic field, it has A1 and it has E. So I have to check what the commutation relation of Q5 or of J05 are with this field. So you first go and look at what happens with the fermion, and what happens is exactly what you expect to happen. So this is just an infinitesimal version of a chiral transformation. So far, nothing unexpected. You can look what happens when you commute G05 with A, and this is 0. Which is what you expected. What goes wrong is when you compute the commutation relation of G05 with the electric field. And it might seem weird because J05 doesn't have any A in it. But indeed, this is not a very intuitive thing because this is a quantum effect. So classically, nothing goes wrong. It's when you start looking at the quantum theory that things go wrong. So what you need to do is actually you need to regulate this theory. And in this way, you will see what happens. So when you regulate this theory, one way to regulate this theory, for example, would be to take these two different fermionic operators and not insert them at the same point, but to insert them at different points. So let me define this. This way I'm making the theory finite, but in this way, it's not gauge invariant anymore because these fermionic fields, they live at different space points. So a gauge transformation will act differently on them. So to make this gauge invariant, I also need to add some small Wilson line that goes from this point to this point. So now you see what goes wrong. So now, when I consider the quantum theory, I have to add some A1. And in this way, J05 and E will not commute anymore. If, of course, Y is between X and X plus epsilon. There's only one thing to show now, And it's that this is not some order epsilon effect that when I take epsilon to 0 goes away. And this is a bit subtle to see. The reason is that, well, it's better if I also say something more, that this goes like JREG itself. But when you go and compute what this regularized version of the current is in the epsilon to 0 limit, actually you see that this diverges. So this has a 1 over epsilon term as a leading term in the epsilon to 0 limit, because you're summing over all the charges, all the particles in the Dirac sea, so you have to do things carefully. There's infinitely many of them. When you do things carefully, you see that you get a 1 over epsilon term. So this is not just some epsilon effect. This actually becomes an order 1 effect. And the final result is that Q5 and E of and the electric field do not commute in the epsilon to 0 limit. Any question?
What happens if you use correlation with the vector current instead? Why does that really that vanishes?
Why are you saying, why is that current conserved?
Yeah, well, suppose you regularize the vector current in the same way.
Yeah, so
Zero.
what you do, for example, is you go and count how many left-handed and how many right-handed particles you have in the Dirac sea with finite epsilon, and then you have to send epsilon to 0. And the charge related to J mu will be the sum of them, and the one related to J mu 5 will be the difference of them. And you see that the epsilon term cancels in one case, and it doesn't cancel in the other one. You can only keep one of these two symmetries, not both. That's the story. Okay, so
Do you have a choice to regularize one of the currents and not the other? Could you choose to make the J5 current conserved but not the vector current?
I think in principle you could, I think. I mean, what I'm doing is I'm choosing a very specific regularization. In this case, this is what happens, but I think in principle you could. Right, no, so then, yeah, so in this, I mean, the statement is that the two U1s, they cannot be both conserved, but by the way I'm doing things, that one cannot be anomalous. Right, thanks. So the only thing that I have left to say about the continuum is that now I can tell you what happens when V alpha when we do a chiral transformation on the Hamiltonian. Remember, we're still in the massless case. But the Hamiltonian will depend on the theta angle, and the only thing that happens is that we get the same Hamiltonian with a shifted theta angle. Alpha is arbitrary here, so I can build this for any alpha. And what I said before, that the theory, the massless theory, doesn't depend on the theta angle, is just the statement that you can do a chiral transformation and you get the Hamiltonian without a theta angle, and the energy spectrum of these two Hamiltonians are the same. So, for example, the energy spectrum doesn't depend on theta at all. This is the Schwinger anomaly. This is something that I ask you to remember because it will come back later in the lattice. So I will remind you, don't worry. But this is what I want to implement on the lattice, basically. Any question before we move to the lattice part? V, this is e to the I alpha Q5. For my... Yeah. I mean, this thing and the d mu J mu not being conserved, J mu 5, are the same thing. Okay, so now let me go on the lattice. I want to put fermions on the lattice, which is always a bit tricky, but we're in one dimension, so it's not that tricky. The reason why it can be tricky is that you have fermion doubling, so you naively put one fermion on the lattice, and you get too many. In this case, in one dimension, you get two fermions on the lattice, because your dispersion relations have also zeros at the end of the brilliance zone. One way to go around this is to consider a lattice where the unit cell is two sides, so you're shrinking your brilliant zone. And this is called staggered fermion. This is something by Kogut and Susskind from the 70s, so this is very well known. The idea is I'm gonna start with my fermion, which has two components, and I will place this, the upper component, on even sides of the lattice, and the odd component, the lower component, on odd sides of the lattice. So this, when I discretize this will become some fermion annihilation operator on even sides, and this one will be on odd sides. That's the idea. My unit cell will be two sides, and I'm going to consider some spin chain with an even number of sides. Now, people in the many-body community know this very well. I think in the high energy physics it's not that appreciated, so let me do something a bit trivial, but that will be instructive for what we do later. So let me take a free fermion, and for some reason, let me discretize and put this on the lattice. Clearly, I don't need to do it, it's a free theory, but this will be the starting point from later. So I like to choose these gamma matrices. And this will be the important guy in this game. So if you do this, let me go to let me compute the Hamiltonian density, because this is what I'm interested in. I get this. This is the Hamiltonian I have. And now I want to do what I just said. I need to put these things on the lattice. My lattice will have some lattice spacing A, and by dimensional reason, I have to add 1 over square root of A here. The only thing I still have to specify is what is this derivative, and this is clearly the discretized version of the usual derivative. But remember that, for example, psi O only lives at odd sides of the lattice. So I'm going to write that this derivative of O will be the usual 1 over square root of A, chi 2n plus 1 minus chi 2n minus 1 over 2a, because these two sides are 2a apart. And I do the same thing with the derivative of psi e. At this point, you have everything that you want to know. You plug it in here, and what you see is that you get the following Hamiltonian. So the kinetic term just becomes some hopping term, some fermionic hopping term, because this is some chi dagger on some sides, and these are the chi's on the two neighboring sides. So when you do this, you get just the usual hopping terms from fermions. And the mass term, instead, it's just acts on only one side, but it has a minus sign depending on whether you're on even or odd sides. So you get this. So this is how you put a free fermion on the lattice if you ever need to. And before I start putting gauge fields in the game, let's discuss what the symmetry of this Hamiltonian is. And I told you that the unit cell is two sides. So if I shift by my system by two sides, so if I send n to n plus 2, what I'm doing is I'm doing a translation. And my theory, I started from a translational invariant theory. This Hamiltonian is invariant under this translation, as I expected. But what happens if I send n to n plus 1? Well, this is not a symmetry unless m is equal to 0, because this term breaks the symmetry between even and odd sides. So this is a symmetry only at m equals 0. And we should think of this as a discrete chiral transformation. Why should we? Well, you see, the way I chose gamma 5 is this one here. So what gamma 5 does is it swaps the two components of the fermion, and I place one component at even sides and one component at odd sides. So gamma 5, what it does is swaps even and odd sides, and this is what a transformation like n to n plus 1 does. So this makes sense that it's only a symmetry at m equals 0 because a chiral transformation is broken at the classical level if m is different than 0. So we should remember that this is a discrete chiral transformation. And now we can start from this and put gauge fields in the game. Any questions so far? Okay, so when we do these sort of things, when we want to discretize lattice gauge theory, the classic thing to do is to have fermions on sides, like I just did, and then to have gauge fields on links. And this is what I'm also going to do. So I will have some spin chain, and these operators chi or chi dagger, they live on the sides, and then I will have some unitary matrix un that lives on the link n, and this is n minus 1, and so on. And we have the un is just a unitary matrix, and we should think of this sort of as the exponential of A1. I need to make the rules of the game. The rules of the game is, I have to tell you what happens under a gauge transformation, and what happens is that chi, the field chi, transform with a phase, as you would expect, and this phase depends on which lattice site you're in, and also U transforms under a gauge transformation, but it picks up two different phases from the side to the left and the side to the right. These are the rules of the game. So this is a U1 theory, so VNs are just phases. I could do this for SUN, and VN would be some other matrix, but these are the rules of the game. And now I want to take the Hamiltonian that I started from, add this gauge field, make it gauge invariant, and it's pretty easy to do that. You see a term like this, the mass term is already gauge invariant. Because when you do a gauge transformation, this guy gives you Vn dagger, and this guy gives you Vn. What is a bit of an issue for now, it's a term like this, because this guy gives you a phase, and this guy gives you a different phase. It's not the inverse of the same phase. So what you need to do when you have fermionic fields on different sides is you need to put a lot of, you need to put a string of UN matrices in between. So an operator like this is gauge invariant. So this is pretty simple. I take this Hamiltonian and I put UN here. And this is, now that the fermionic hopping term is fine, the only thing I need to put in the game now is a kinetic term for the gauge field. And this is pretty easy to do. You don't need to stagger anything. What you do is you add a term like this. Just by seeing what happens in the continuum, you add this. So what is ln? ln is the discretized version of the electric field. ln measures the electric field on a link. So the commutation relation here are the usual one for the fermion, and ln and un, instead they have this. So increases the electric field by 1, while dagger, that's in here, decreases the electric field by 1 on a given link. So this is basically everything I need. Now I want to study this spin chain. This is the discretized version of the Schwinger model, and I want to study this. I need to tell you just a few more things, and then I can just start doing numerics. But the few things are, what do I mean by a gauge invariant state? I told you what a gauge invariant operator is, but I haven't told you, I get states by acting with these operators on the vacuum. I have to tell you how the vacuum transforms under a gauge transformation, so I'm gonna do this now. I have to tell you what I think, what I'm thinking of in terms of boundary conditions, and then I have to tell you what is the continuum limit that I'm interested in. So if you think of the continuum, what you have is that the electric field, its derivative, the electric field, looks like the fermion, is the fermion density, roughly speaking. I want to do something like this as well. So the idea is that if I have some site with some charge Q, then the difference between ln and ln minus 1 will just be the charge Q. This is called Gauss Law. Gauss Law. What I want to do is to implement invariance under small gauge transformation, and this is what it does. But I haven't told you what Qn is. It has to look like the number operator on the site, but actually there's some ambiguity, which is some normal ordering ambiguity, that allows me to add a constant to it. Now, I can do several things, but what I'm interested in is doing what everybody else does, because what I will say has some implication on papers that take this specific choice of constant. So what most people do, and by most I mean all but one paper that I know of, is to choose this constant like this. Okay, cool. I think there was a paper last week as well that then they chose the other one. The other paper, they choose -1/2, which is a bit weird in one sense, in the sense that you expect the eigenvalues of ln to be integer. But if you choose a half, well, then they will not be. But it's fine, they can do it. And what I'm going to say does not apply to them being Berruto, Grignani, Semenov, and somebody else from the 90s. But everybody else uses this choice. So I'm going to consider this choice. And this is rather subtle, but this is the whole point that I will be discussing later. Okay, so one dimension is very easy because I have this ln, but I can always express it in terms of fermionic operators, and if I have, for example, open boundary condition, I just get rid of my gauge field, and I end up with a Hamiltonian that just depends on fermions, but will be non-local. But this is one of the advantages of being in 1D, is that you can integrate out almost completely the gauge field. Now, I have to tell you about open or periodic boundary conditions. I'm going to consider both of them when I do numerics. Let's start with the simplest one. Open boundary condition, you start with having 0 gauge field, and then L0 will just be given by whether I have a fermion here or not. And then L1 will also be given by if I had fermions here and there or not. So you just integrate out with open boundary conditions. You completely integrate out the gauge field. And so if I have well, when I get to the end of the chain, though, I want to go back to 0 electric field. So when you sum the Gauss law over all sides of the chain, you get that the sum over the charges has to be equal to 0, which means that we're working at half filling. So I have n/2 fermions in my spin chain. Remember that n is always even because my unit cell is 2 sides. So if I do this and I work at finite n, then I have n/2 gauge invariant states. So I have a finite gauge invariant Hilbert space at finite n. This is nice. But we like periodic boundary conditions because we like to have translations as actual symmetries of our theory. And with periodic boundary condition, the situation is a tiny bit more tricky, but not that much. So say that I start from some L0, then L1 will be completely determined by what L0 was and what the fermionic occupation number of this site was. And then L2 will be given by L0 and the fermionic occupation number and so on. So here, we actually are left with an extra degrees of freedom, which could be L0, which actually can take infinitely many values. So let me choose a nicer way to parameterize this. Let me take the fermionic, the average electric field, like this. Then my gauge invariant states will be given by epsilon, and then you write down the occupation number. So epsilon can take infinitely many values, so even though I'm working at finite n, I have an infinitely dimensional Hilbert space. This is not ideal, but what I'll do is I'll truncate in epsilon between some upper and lower value, and then I will take this to be large enough, and things converge exponentially fast with this, so we shouldn't worry about this. And again, the Gauss law, summing Gauss law over all the sites gives you the condition Ln is equal to L0 when you go around the loop. And you need to have half-filling as well to satisfy this. And another slightly more subtle thing is that these ln's are integers. Okay, this is pretty simple.
Question.
Yes?
Yeah, is chiral symmetry of the lattice model and the chiral symmetry of the continuum model are not quite the same?
I agree.
Yeah, okay, good.
I will say more things in just a second. So now what I'm interested in is I want to take the continuum limit, which is pretty simple. I take the lattice space into 0 and the number of sides to infinity, so that the length of the circle, if I'm at periodic boundary conditions, is fixed. Okay. This is what I want to do. Now I have all the recipes to go and put this on a computer and get some numerics. But first I would like to discuss, chiral symmetry on the lattice. And let me keep this. So I told you two things before that I need. I told you that in the continuum you have this property at m equals 0. Oh, let me do one thing before. Let me, for a second, call the lattice mass m lat to make it clear that it's not the continuum mass. So in the continuum, we had this. And I told you that when we didn't have any gauge field, n going to n plus 1 looks like a discrete chiral transformation. So now let me do this same discrete chiral transformation now that I have a gauge field in the game. And so let me consider the operator v that implements this. So it sends chi n to chi n plus 1. You remember how I defined the charges, so this sends Qn to Qn plus 1 plus minus 1 to the n. And I want this transformation to leave me in the gauge invariant Hilbert space, so I had to satisfy Gauss's law. So Ln gets then to Ln plus 1 plus a constant. Okay, so I know what V does. My Hamiltonian only depends on these things, so I can just see what happens when I apply V to H of theta on the lattice. And what I see is that this gives me H of theta plus pi plus some term. And this term, I'm just going to tell you what the end thing is, depends on this coefficient. times some operator. This you get while using Gauss Law, but I'm only interested in gauge invariant states, so it's fine. So you see that if I choose the lattice mass to be minus e squared a over 8, then what I have on the lattice is that v h theta v minus 1 is equal to h theta plus pi. So this looks like a discrete version of the Schwinger anomaly, but as you notice, we had the Schwinger anomaly only at m equals 0. Here we have a non-zero lattice mass. So the claim is that the lattice mass and the continuum mass are not the same thing. They are related by a mass shift. So this is our main result. Conceptually, this follows from this consideration, but you might say, okay, but this is not important. I'm interested in the continuum limit. In the continuum limit, a goes to 0, so this is some subleading thing. So eventually, if your computer is powerful enough, you don't care. You can take whatever m you want, this one without the mass shift or not, and you will see the same thing. And it's true, but your convergence will look much, much better if you make this choice. And now I will show you some numerics that show indeed this much better convergence. Any question? Okay, so now I need the slides. Sorry? I expect things, when you send a to 0, I expect some things to converge with quadratically in A rather than linearly in A once you do this shift. But this is a mix of what I expect to be in some very simple case and just looking at the numerics. So I will show you. I think that's the easiest thing.
There is no, there is no way, like, say, this is one power or not before doing the numeric.
There might be a way. I am not sure though.
Is there an original theory which takes h to minus h?
H, the Hamiltonian,
Yeah.
to minus H.
Like Chiral Transformation, CH, C minus 4.
It wouldn't take H to minus H. It would swap what you call electric field. So like,
Just wondering whether you, in conventional interpretation
Mhm.
with the direct C, there's this sort of thing which maps positive states to the negatives.
yes. So I will show a phase transition at some point where you have some Z2 breaking, and the Z2 I think it's like taking positive electric field and sending it to negative electric field. So maybe this is what you're talking about. So, yes, how do I do full screen? Okay. Okay, so I'm gonna do some very easy numerics to start off, and by very easy, I mean really easy. I'm gonna take periodic boundary conditions because I like translational invariance, and I'm gonna work at finite n, diagonalize the theory, and then do it for larger n, and then extrapolate to n to infinity. As I told you, I need to truncate this epsilon variable because otherwise my gauge invariant Hilbert space is infinitely dimensional, and I truncated between some epsilon max and some minus epsilon max and some epsilon max. And this is not a very hard thing to do because things converge exponentially with this. So I will take in practice 5.5, and we see that if we change it by a bit, nothing changes in our result. And I'm gonna start from the smallest chain I can consider and go up to 18, and then extrapolate to n to infinity. And to give you an example, all the way up to n equal to 12, you can easily do it on your laptop. The rest we did it on the cluster, but I think even n equal 14, you could do it just on your laptop. So these numerics that I'm gonna show are very easy, but I just want to show you that things work the way we expect. So No, it's discrete. It's rather, roughly speaking, it will be like 1 over n times an integer. Because you're computing these are integers and you're summing a bunch of integers and dividing by n. So I told you that the theory is free at m equals 0. Let me show you that we see a free theory. This is the radius of the circle times the electric charge to make something dimensionless. I look at a fixed n, I fix L, and I look at some n, and then I look at a higher n, and then I extrapolate to n to infinity. You see these things are fit with n to infinity, so they have some error bars, but they're pretty small in the case where L is small. And what you see is what you expect from a free theory. You see 1 particle states, 2 particle states, 3 particle states, and these are states with no momentum. You also have states with momentum that go around the circle, and the lowest one will be 2 pi over L, and this will be a 1 particle state with non-zero momentum. So this is what we expect to see, this is what we see. This is very nice. Now let me compare how doing numerics with the mass shift or without the mass shift goes. So when you take n to infinity, you will see the same result. But let's work at finite n to see how things converge. So this is the fermionic, the fermion bilinear condensate, which we know analytically because, again, we're at m equals 0, so it's this orange line. If we do the numerics without the mass shift, we have these triangles here, so this is n equal 4, this is n equal 10. Eventually, we'll converge here. Okay. If we do the mass shift instead, we're already very, very well converged at n equal 10. You see, n equal 10 is basically all the way to here, it's basically already on the line. So this is, doing this numerics or doing this numerics is the same level of difficulty, but just one is smarter because you're using this mass shift. And this mass shift makes convergence much, much faster. But let me tell you something a bit more interesting, because m equals 0 is just a free theory, so I would like to say something in a theory that's not free. And let me consider this, there's a phase transition in this model. I'm gonna take theta equal pi. I could also take theta equal 0, but it's the same. If I have a very negative, large and negative mass, you can see that I just have 1 vacuum. If I take a very large and positive mass, you see that you have 2 vacuums. And they have sort of non-zero average electric field. So this is what I was saying when there is a Z2 breaking. This is just has this effective epsilon, which is just epsilon plus the theta angle, to be 0 in this limit, and this one has a non-zero. So this is some Z2 breaking. We expect this to be in the same. So we know that there's already evidence that this is a continuous phase transition, and we expect this to be in the Ising universality class. And now I will see this. We're going to do things a bit differently. So first, we're going to send n to infinity and then a to 0. So I'm not on a finite size circle. I'm on an infinitely large circle. But let me start again with some easy numerics. So this is, again, same thing I said before. You go all the way to n equal 18, and then you extrapolate to n equal infinity. And we have this orange result is some numerical result, which I'm going to discuss next. But it's very precise, so we should compare with this. If we don't do the mass shift, we see that when we take a to 0, we end up in the same ballpark, but we're converging linearly with a. If we do the mass shift instead, we're way closer to the a to 0 result, and it looks like it's converging like a squared. And this buys you a lot of precision when you do the fit of a to 0. So, for example, this is the number that we got. This was the number that people had when they considered the system first. So yeah, it looks like it improves. Even if we're a non-zero mass, we're improving we're improving our precision by a lot. But the best results, they come from DMRG, so these tensor network methods that people use. So we also did DMRG. And before, people, in 2002, there was this paper that considered this, and they found the value of the critical mass to be this number here. We did the same using the MRG and the mass shift, and we beat their precision by 1 digit. And we didn't try that hard. We tried a bit, but not super hard. So we could get even a more precise result than this, but this is due to the mass shift. And Well, maybe you notice that this looks like a third. We don't know why. This really looks like a third. Maybe it's a third. Maybe there's some reason why this critical mass is a third, and what we're doing is just computing numerically all the digits to a third, which would be pretty stupid to do. But right now we don't know why it looks like a third. So, you know, nice things can happen in 1 plus 1D, so maybe there's some reason for this to be a third. I told you that this should be Ising, and it indeed looks like Ising, and the way to see this is you go at the critical mass, and then you go and look at the energy levels on the cylinder, and they should be related to the dimension of operators in the CFT. But this is true only in the L to infinity limit, so when the circle is infinitely large, because Ising describes the long-range physics of this model, but I have some IR cutoff, so I should send this IR cutoff to infinity. So with this in mind, let's look at what the energy levels look like. We see some 1/8 energy level that's pretty well converged, and then we see the next energy level gets closer and closer to 1, and well, it looks like it's converging to 1. We didn't push to larger radius, so okay, that's pretty. I think that's pretty convincing that we're in the Ising universality class. And now let me tell you, I told you at the beginning that I would be talking about symmetry that sometimes are anomalous and sometimes are not, but I've only been talking about anomalous symmetry, so now it's time to relax. We can have real symmetries for a bit. So I'm going to consider a few other models that look similar to this. And one of them is the charge Q Schwinger model, where the fermion does not have charge 1, but it has charge Q, where Q is some integer. So what you do actually, there's no numerics to do here. All the numerics I've done before, they translate to this. You just need to rescale some parameters. What you do at the level of the Hamiltonian is you rescale the charge by Q, of course, because your fermion has Q charge Q now. The hopping term, for example, look like this. Now we have to add UN to the Q, so if a fermion hops, the electric field will go up or go down by Q, not by 1. Okay, that's pretty simple. If you do the numerics with this shift, so we shift the theta angle and E by some value of Q, then we just get the same thing as before, and our mass shift now will have an extra Q square in front. The numerics are exactly the same, so doing this mass shift increases your convergence, but improves your convergence by a lot. What is different, though, and I think this is why this model is interesting, is the symmetry interpretation. So V, you remember, is the guy that does the shift by one side. If I have charge 1, then it shifts the theta angle by pi. If I have charge Q, it will shift the theta angle by Q pi. And the theta angle is identified with period 2 pi. So if I take even Q, this doesn't do anything to the Hamiltonian. So even Q, we actually have a Z2 symmetry. It's not some anomalous symmetry. For even Q, we have something nice. So this is nice to think of because of the symmetry interpretation. And we know that the massless charge Q Schwinger model in the continuum has a ZQ1 cross ZQ symmetry. And if we have even Q, then on the lattice, we're breaking this to ZQ1 cross Z2. So why do we have this? Well, we have a one-form symmetry ZQ, which means that I have one topological operator, which just measures what the electric field is mod Q. Since the electric field can only change by Q, plus or minus Q, then the electric field mod Q is the same on all sides of your lattice. And this is the operator. So here I insert it at site n, but it doesn't matter at which site I insert it. It's the same on every site of a state. So this commutes with the Hamiltonian, and it tells you that the Hamiltonian, the Hilbert space, splits in different sectors, which people call universes, and there's Q of them. Now, if Q is even, we see that the operator V, which does the discrete Chiral transformation, anti-commutes with W, which tells you that if I act with V, then I am going from the mth universe, which means that the electric field is mod Q is equal to M, to the M plus Q over 2 universe. So I'm moving to a different universe, but since V commutes with the Hamiltonian, I'm not changing the energy of the state. So these two universes will be exactly degenerate, and this is this Z2. Something else that I can do is I can generalize this model by taking, instead of one fermion, an F fermions. And this is something that we're doing currently. Again, we have that the theta angle is shifted by NF. So if I take an F equal to 2, then it's a true symmetry. And we see that the convergence of the numerics, you can still do the mass shift. You can see that the convergence of the numerics increases dramatically, maybe even more than before. So now we're considering this model using metric product states and DMRG. And let me conclude with a sad note. If you're interested in non-abelian gauge theories, maybe you got excited and you said, oh, I want to use this mass shift. But it's not clear if there's something like this. The reason is that the Gauss law, when people consider non-abelian gauge theories in 1 plus 1D, is not staggered. So you remember I had written back here that the charge would have a minus 1 to the n term. And the Gauss law would depend on this. So when you do non-abelian gauge theories in 1 plus 1D, this is not the case. So there's not an obvious way to do this in gauge theories, or if you want, there's no need to do this in gauge theories. You can still study this with matrix product states or with tensor network methods. People have done SU2 and SU3 with fundamental fermions. They get really good results because these methods are really nice. So you can still study them. And after the sad note, let me end with a more positive note, which is what happens if you think at higher dimension. So you're interested maybe in QED in 3 dimension. Well, you can define this again with staggered fermions on a 2-dimensional lattice. And when people do this, at least some of the papers I have seen, people define the Gauss law to be like this. So now in 2 dimension, you cannot just get rid of the gauge field because, okay, you're in 2 dimension. But this depends on some charge, which again is defined in a staggered way. So now sites depend on 2 indices, and there's a -1 for some sites which are like the even or the odd ones. So it looks like in this case, you also need, or you also should take some mass shift in order to have better numerics. So maybe doing numerics with this, with the methods we have, is something that at the moment we cannot do, that I don't know yet. But you can also consider, for example, strong coupling expansion. And I told you that strong coupling expansion, if you don't know what it is the opposite of the continuum limit. But sometimes you can do it, and then you can do some resummation, some Padera resummation, and you get very nice result. In the case of the Schwinger model, you do get results with like less than 1% difference after you include the mass shift. Since the mass shift is not subleading in this in the strong coupling limit, if you want to do strong coupling expansion, you really need to use it. And I think this is what I wanted to say. Thanks a lot for your attention.
Yes, Luca?
Did you try finding a Kramer's linear duality to realize
Kramer's veneers for what?
some kind of duality that you, let's say you wanted to prove FC equals 1/3?
Aha, I see. No, I have not tried, but I would imagine that that's sort of one of the ways to do things, like to map something to some known Ising, critical Ising or something, but only at this point, or to look for some duality, something like this. So, no, we haven't tried. Non-integer Q. Why do you want to do that? Sorry? I don't think you can. One thing you could do, for example, is consider charge Q with integer Q, and then consider some external quark. Say, for example, you take a charge to fermion, and then you say, oh, what happens if I insert some external probe charge 1 quark? And that looks like doing some fractional charge, but I think that that would be the clean way to do it. But maybe you have something more precise in mind. I'm not sure.
So do you understand in practice why this shift changes so dramatically in the convergence?
So I think that in some cases that I've seen, the point after you do the mesh shift is symmetric under sending A, the lattice spacing, to minus A. I don't know what this means physically, but I saw that you're in a point that's symmetric, that has, like when you expand around this point, things will go like A squared, not with A. So when I show convergence here, this is what I expected. I didn't expect, since I'm expanding around a point that's symmetric under flipping the sign of A, I expected this only to behave like A squared, while this one is not, and this goes like A. I don't have a precise way of saying this, but when you go and compute, this was something in the small circle limit. So if you take A to 0 but keeping n fixed, for example, then you have weak coupling and you can do some things by hand. And in that case, I would see that this point look nicer because of A to minus A was a symmetry of this point. That's my vague intuition.
Wait, but is it just because your mass shift is linear in A? Or the bottom curve is just...
Yeah, right. Yeah, so the mass shift is linear in A, so if you start from this point, then you expect to introduce an A in here. But the non-trivial statement is to say that this point will only have A square things. But yeah, I agree. I mean, once you say that, then you understand why this goes like 1 plus A. Yeah.
Okay, let's thank Bernardo again.
Thank you.
And we meet again at 11:30.